3. Induction of electromotive forces. A closed conductor convolution or turn, revolving in a magnetic field, passes during each revolution through two positions of maximum enclosure of lines of magnetic force, labeled A in Figure 4, and two positions of zero enclosure of lines of magnetic force, labeled B in Figure 4. Thus, it cuts during each revolution 4 times the lines of force enclosed in the position of maximum enclosure. If phi represents the maximum number of lines of force enclosed by the conductor, and n is the number of complete revolutions per second, or cycles, and n is the number of convolutions or turns of the conductor, then the lines of force cut per second by the conductor, and thus the average induced electromotive force is equal to 4 times nn phi absolute units, or 4 nn phi times 10 to the power of minus 8 volts. If n is given in hundreds of cycles, and phi is in millilines, then the electromotive force is equal to 4 nn phi volts. If a coil revolves with uniform velocity through a uniform magnetic field, the magnetism enclosed by the coil is equal to phi cosine phi, where capital Phi is the maximum magnetism enclosed by the coil, and lowercase phi is the angle between the coil and its position of maximum enclosure of magnetism, as shown in Figure 5. The electromotive force induced in the coil, which varies with the rate of cutting or change of phi cosine phi, is thus equal to E naught sine phi, where E naught is the maximum value of electromotive force, which takes place for phi equal to 90 degrees, or at the position of zero enclosure of magnetic flux. Since the average value of sine phi is 2 divided by pi, the average induced electromotive force is equal to 2 over pi times E naught. Since, however, we found above that E equals 4 nn phi is the average induced electromotive force, it follows that E naught equals 2 pi nn phi is the maximum. And since small e equals 2 pi nn phi sine phi, the instantaneous induced electromotive force, now continuing, with uniform rotation, the angle phi is proportional to the time t, so phi equals 2 pi nt. Giving t equals 1 over n, the time of one complete period or revolution in a bipolar field, or 1 over p of one revolution in a 2p polar field. Thus phi equals 2 pi nt. Therefore, E equals 2 pi nn phi sine 2 pi nt. If the time is not counted from the moment of maximum enclosure of magnetic flux, but t1 is the time at this moment, we have E equals 2 pi nn phi sine 2 pi n times t minus t1. Or E equals 2 pi nn phi sine of phi minus phi 1, where phi 1 equals 2 pi nt1 is the angle at which the position of maximum enclosure of magnetic flux takes place and is called its phase. These electromotive forces are alternating. If at the moment of reversal, the connections between the coil and the external circuit are reversed, the electromotive force in the external circuit is pulsating between 0 and E naught, but has the same average value E. If a number of coils connected in series follow each other successively in their rotation through the magnetic field, as the armature coils of a direct current machine, and the connections of each coil with the external circuit are reversed at the moment of reversal of its electromotive force, their pulsating electromotive forces superimposed in the external circuit make a more or less steady or continuous external electromotive force. The average value of this electromotive force is the sum of the average values of the electromotive forces of the individual coils. Thus, in a direct current machine, if phi equals maximum flux enclosed per turn, and n equals total number of turns in series from commutator brush to brush, and n equals frequency of rotation through the magnetic field, then E equals 4 nn phi is the induced electromotive force, with phi in megalines, n in hundreds of cycles per second. This is the formula of direct current induction. Examples. 1. A circular wire coil of 200 turns and 40 centimeters mean diameter is revolved around a vertical axis. What is the horizontal intensity of the magnetic field of the Earth if at a speed of 900 revolutions per minute the average electromotive force induced in the coil is 0.028 volts? The mean area of the coil is 40 squared pi over 4 equals 1255 square centimeters. Thus the terrestrial flux enclosed is 1255 times x, and at 900 revolutions per minute, or 15 revolutions per second, this flux is cut 4 times 15, or 60 times per second by each turn, or 200 times 60 equals 12,000 times by the coil. Thus, the total number of lines of magnetic force cut by the conductor per second is 12,000 times 1255 times x equals 0.151 times 10 to the power 8x, and the average induced electromotive force is 0.151 x volts. Since this is 0.028 volts, x equals 0.186. Example. Example 2. In a 550-volt direct current machine of 8 poles and 500 revolutions with drum armature, the average voltage per commutator segment shall not exceed 11. Each armature coil shall contain one turn only, and the number of commutator segments per pole shall be divisible by 3 so as to use the machine as a three-phase converter. What is the magnetic flux per field pole? 550 volts at 11 volts per commutator segment gives 50, or as next integer divisible by 3, n equals 51 segments or turns per pole. 8 poles give 4 cycles per revolution, 500 revolutions per minute, or 500 over 60 equals 8.3, 3 revolutions per second. Thus the frequency is n equals 4 times 8.3, 3 equals 33.3 cycles per second. The induced electromotive force is 550 volts. Thus, by the formula of direct current induction, E equals 4nn phi, or 550 equals 4 times 33.3 times 51 times phi. Thus phi equals 8.1 millilines per pole. Example 3. What is the electromotive force induced in a single turn of a 20-pole alternator revolving at 200 revolutions per minute through a magnetic field of 6.4 millilines per pole? The frequency is n equals 20 times 200 over 2 times 60 equals 33.3 cycles. Now small e equals E naught sine phi, and E naught equals 2 pi nn phi, with phi equals 6.4, n equals 1, and n equals 0.333. Thus, E naught equals 2 pi times 0.333 times 6.4 equals 13.3 volts maximum, or E equals 13.3 sine phi. Section 4. Effect and effective values. The effect or power of the continuous electromotive force E producing continuous current I is P equals EI. The electromotive force consumed by resistance R is E1 equals IR. Thus the effect consumed by resistance R is P equals I squared R. Either E1 equals E, then the total effect of the circuit is consumed by the resistance, or E1 less than E, then only a part of the effect is consumed by the resistance, the remainder by some counter-electromotive force E minus E1. If an alternating current I equals I naught sine phi passes through a resistance R, the effect consumed by the resistance is I squared R equals I naught squared R sine squared phi, which equals I naught squared R over 2 times the quantity 1 minus cosine 2 phi. Thus it varies with twice the frequency of the current, between 0 and I naught squared R. The average effect consumed by resistance R is average of I squared R equals I naught squared R over 2, which equals I naught over square root of 2 squared times R. Since the average of cosine is 0, thus the alternating current I equals I naught sine phi consumes in a resistance R the same effect as a continuous current of intensity I equals I naught over square root 2, approximately 0.707 times I naught. The value I equals I naught over square root 2 is called the effective value of the alternating current I equals I naught sine phi, since it gives the same effect. Analogously, E equals E naught over square root 2 is the effective value of the alternating electromotive force E equals E naught sine phi. Since E naught equals 2 pi nn phi, it follows that E equals square root 2 pi nn phi, which equals 4.44 nn phi. The effective alternating electromotive force induced in a coil of n turns rotating with frequency n in hundreds of cycles through a magnetic field of phi megalines of force. This is the formula of alternating current induction. The formula of direct current induction, E equals 4nn phi, holds also if the electromotive forces induced in the individual turns are not sine waves, since it is the average induced electromotive force. The formula of alternating current induction, E equals square root 2 pi nn phi, does not hold if the waves are not sine waves, since the ratios of average to maximum and of maximum to effective electromotive force are changed. If the variation of magnetic flux is not sinusoidal, the effective induced alternating electromotive force is E equals gamma square root 2 pi nn phi. Gamma is called the form factor of the wave and depends upon its shape, that is the distribution of the magnetic flux in the magnetic field. Examples. 1. In a star-connected 20-polar three-phaser, revolving at 33.3 cycles or 200 revolutions per minute, the magnetic flux per pole is 6.4 millilines. The armature contains one slot per pole in phase, and each slot contains 36 conductors. All these conductors are connected in series. What is the effective electromotive force per circuit, and what the effective electromotive force between the terminals of the machine? 20 slots of 36 conductors give 720 conductors, or 360 turns in series. Thus, the effective electromotive force is E1 equals square root 2 pi nn phi equals 4.44 times 0.333 times 360 times 6.4 equals 3,400 volts per circuit. The electromotive force between the terminals of a star-connected three-phaser is the resultant of the electromotive forces of the two phases, which differ by 60 degrees, and is thus 2 sine 60 equals square root 3 times that of one phase. Thus E equals E 1 times square root 3 equals 5,900 volts effective. Example 2. The conductor of the machine has a section of 0.22 square centimeters and a mean length of 240 centimeters per turn. At a resistivity of copper, rho equals 1.8 times 10 to the minus 6. What is the electromotive force consumed in the machine by the resistance, and what the energy consumed at 450 kilowatt output? 450 kilowatt output is 150,000 watts per phase or circuit. Thus, the current I equals 150,000 over 3,400 equals 44.2 amperes effective. The resistance of 360 turns of 240 centimeter length, 0.22 square centimeter section, and 1.8 times 10 to the minus 6 resistivity is R equals 360 times 240 times 1.8 times 10 to the minus 6 over 0.22 equals 0.71 ohms per circuit. 44.2 amps times 0.71 ohms gives 31.5 volts per circuit, and 44.2 squared times 0.71 equals 1400 watts per circuit, or a total of 3 times 1400 equals 4200 watts loss. Example 3. What is the self-induction per wire of a three-phase line of 14 miles length, consisting of 3 wires number knot double knot, diameter 0.82 centimeters at 45 centimeters apart, transmitting the output of this 450 kilowatt 5900 volt three-phaser? 450 kilowatts at 5900 volts gives 44.2 amperes per line. 44.2 amperes effective gives 44.2 times square root 2 equals 62.5 amperes maximum. 14 miles equals 22,300 meters. The magnetic flux produced by 1 ampere in 1,000 meters of a transmission line of 2 wires 45 centimeters apart and 0.82 centimeter diameter was found in paragraph 1, example 3, as 2 phi equals 0.188 times 10 to the 6th I, or phi equals 0.094 times 10 to the 6th I for each wire. Thus, at 22,300 meters and 62.5 amperes maximum, it is per wire phi equals 22.3 times 62.5 times 0.094 times 10 to the 6th equals 131 millilines. Hence, the induced electromotive force effective value at 33.3 cycles is E equals square root 2 pi n phi equals 4.4, 4 times 0.333 times 131 equals 193 volts per line. The maximum value is E naught equals E times square root 2 equals 273 volts per line. And the instantaneous value E equals E naught sine phi minus phi 1 equals 273 sine phi minus phi 1. Or since phi equals 2 pi nt equals 210 t, we have E equals 273 sine 210 times t minus t1. Section 5. Self-induction and mutual induction. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in the circuit is called the inductance of the circuit. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in a second electric circuit is called the mutual inductance of the second upon the first circuit. It is equal to the mutual inductance of the first upon the second circuit, as will be seen, and thus called the mutual inductance between the two circuits. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in this circuit and not interlinked with a second circuit is called the self-inductance of the circuit. If I is the current in a circuit of n turns, and phi is the flux produced thereby and interlinked with the circuit, then n phi is the total number of interlinkages, and L equals n phi over I is the inductance of the circuit. If phi is proportional to the current I and the number of turns n, then phi equals Ni over rho, and L equals n squared over rho. Rho is called the reluctance, and Ni the magnetomotive force of the magnetic circuit. The reluctance rho has in magnetic circuits the same position as the resistance R in the electric circuit. The reluctance rho, and thus the inductance, is constant only in circuits containing no magnetic materials as iron and so on. If ρ1 is the reluctance of a magnetic circuit interlinked with two electric circuits of N1 and N2 turns respectively, the flux produced by unit current in the first circuit and interlinked with the second circuit is N2 over ρ1. And the mutual inductance of the first upon the second circuit, thus M equals N1 N2 over ρ1. That is equal to the mutual inductance of the second circuit upon the first circuit as stated above. If ρ1 equals ρ, that is, no flux passes between the two circuits, and L1 is the inductance of the first, L2 the inductance of the second circuit, and M equals mutual inductance, then M squared equals L1, L2. If ρ1 is greater than ρ, that is flux passes between the two circuits, then m squared is less than L1, L2. If ρ1 is less than ρ, that is flux passes between the two circuits, then m squared is greater than L1, L2. Thus, if L1 and L2 are the inductances of the two circuits, L1 over N1 and L2 over N2 is the total flux produced by unit current in the first and second circuit respectively. Of the flux L1 over N1, a part S1 over N1 is interlinked with the first circuit only, and S1 is called its self-inductance, and the part M over N2 interlinked with the second circuit also, where M equals mutual inductance. And L1 over N1 equals S1 over N1 plus M over N2. Thus, if L1 and L2 are inductance, S1 and S2 are self-inductance, and M is mutual inductance of two circuits of N1 and N2 turns respectively, we have L1 over N1 equals S1 over N1 plus M over N2, and L2 over N2 equals S2 over N2 plus M over N1, or L1 equals S1 plus N1 over N2 times M, and L2 equals S2 plus N2 over N1 times M. Or M squared equals the product of L1 minus S1 and L2 minus S2. The practical unit of inductance is 10 to the power 9 times the absolute unit, or 10 to the power 8 times the number of interlinkages per ampere, since 1 ampere equals 0.1 unit current, and is called the Henry. 0.001 of it is called the millihenry. The number of interlinkages of I amperes in a circuit of L Henry inductance is IL times 10 to the power 8 lines of force turns, and thus the electromotive force induced by a change of current di in time dt is equals minus di over dt times 10 to the power 8 absolute units. A change of current of 1 ampere per second in the circuit of 1 Henry inductance induces 1 volt. Examples. 1. What is the inductance of the field of a 20-polar alternator? If the 20 field spools are connected in series, each spool contains 616 turns, and 6.95 amperes produces 6.4 millilines per pole. The total number of turns of all 20 spools is 20 times 616 equals 12,320. Each is interlinked with 6.4 times 10 to the 6th lines. Thus, the total number of interlinkages at 6.95 amperes is 12,320 times 6.4 times 10 to the 6th equals 78 times 10 to the 9th. 6.95 amperes equals 0.695 absolute units, hence the number of interlinkages per unit current, or the inductance, is 78 times 10 to the 9th over 0.695 equals 112 times 10 to the 9th equals 112 henries. Example 2. What is the mutual inductance between an alternating transmission line and a telephone wire carried for 10 miles below and 1.20 meters distant from the one, 1.50 meters distant from the other conductor of the alternating line? And what is the electromotive force induced in the telephone wire if the alternating circuit carries 100 amperes at 60 cycles? The mutual inductance between the telephone wire and the magnetic circuit is the magnetic flux produced by unit current in the telephone wire and interlinked with the alternating circuit. That is, that part of the magnetic flux produced by unit current in the telephone wire, which passes between the distances of 1.20 and 1.50 meters. At the distance x from the telephone wire, the length of magnetic circuit is 2 pi x. The magnetizing force F equals I over 2 pi x, if I equals current in telephone wire in amperes, and the field intensity H equals 0.4 times pi F equals 2I over x, and the flux in the zone dx d phi equals 2I over x times dx. For length L equals 10 miles equals 16 10 times 10 to the power 8 centimeters. Thus, phi equals the integral from 120 to 150 of 2I over x dx, which equals 322 times 10 to the 8th I log of 150 over 120, equals 72 times 10 to the 8th I, or 72 times 10 to the 8th interlinkages. Hence, for I equals 10, or 1 absolute unit, thus m equals 72 times 10 to the 4th absolute units, equals 72 times 10 to the minus 5th, henries equals 0.72 millihenry. 100 amperes effective, or 141.4 amperes maximum, or 14.14 absolute units of current in the transmission line, produces a maximum flux interlinked with the telephone line of 14.14 times 0.72 times 10 to the minus 5 times 10 to the 8th equals 10.2 millilines. Thus, the electromotive force induced at 60 cycles is E equals 4.44 times 0.6 times 10.2 equals 27.3 volts effective.